able to track the relevant objects. So here's where the person might have given the text that the things you care about are the succulent and the llama, and so that's what's being tracked. It's also where we actually track the point flow, so what the trajectory looks like that the object goes through, and then a hand tracker to be able to take the hand out of the video. And it uses these vision foundation models to extract an object-centric representation, meaning that it uses these sort of existing packages to segment out the objects, and then builds a representation that abstracts away the changes in contact points between the hand and the object. So this sequence would be the hand touches the succulent, the hand moves the succulent to the llama, all of the objects are in contact, and then the hand releases. And by mimicking at that level of abstraction, we're able to generalize. And I'll just show this last slide on this topic, where the video demonstration was just shown there on the left, and then the robot, even though the background looks very different. Yeah, I'll see if I can speed this up a little bit. There we go. Even though the background looks different, the camera angle is different. Maybe even the object starts on top of this boat instead. From that single object, that demonstration, the robot's able to mimic it, and so it sort of warps the trajectory and changes, so that it matches the start and end points. And here you see a longer video demonstration where it involves multiple objects, and again, the robot is able to mimic it in different backgrounds and lighting conditions, even in extreme lighting conditions. Again, because the visual perceptual systems are able to handle that, and it's even, since we use language annotations, if the demonstration used a mug and then there's a different looking mug in the image, it's still able to work. And so that's what was shown here. And I saw the question about which vision foundation model we're using. We're basically, these are the full references are in the paper. It's on archive right now. It's under review. But this is a track any points model, and there's I can't remember the hand tracking system, and this is the VOS object tracking system. But you can get full details in the paper. So that's just a brief aside. Like I say, there's a full version of the talk on this on my website. But the main advertised topic for today is outracing champion Gran Turismo drivers with deep reinforcement learning, and so that's what I'm going to focus on for the rest of the talk. And this is work that I did do in my capacity as chief scientist at Sony AI, and it's done with a large team a fantastic team of collaborators. So this is all of the co-authors on the paper. It was actually the original paper, which was published on the cover of Nature in 2022. Like I say, this comes out of Sony AI, which was established in 2020. And within 2 years, we were able to reach this sort of landmark result, which was the first time that an AI program was able to beat the best people at a real-time control task, in a task that people really care about. In that there's like esports competitions, people have put in their 10,000 hours to become really good at this. And throughout this talk, in the videos I show you and in the diagrams I show you, GT Sophie, which is our agent, is always going to be a colored car, and the cars showed in white are going to be driven by human drivers. So you'll be able to easily tell the difference. And the thing that I think really marked the success here was I think very similar to the chess and the Go and the Jeopardy and the poker results in the past, was that there was, first of all, a lot of computation, a really well-engineered compute architecture, which I'll talk a little bit about, a lot of data, some really top-notch engineering, and then a few sort of algorithmic and methodological insights that were sort of the key sort of secret sauce that made it so we could get over the edge. And that's sort of what's I wouldn't say secret sauce, because it's what we published on in the Nature article, but the sort of the thing that makes it not just raw computation, but sort of makes it get over the edge of being able to beat the best people. So this was a partnership between Sony AI, which was my group, Polyphony Digital, which is the group that makes the video game, and Sony Interactive Entertainment, which is the the PlayStation Group at Sony. And I'll talk a little bit about I'll talk a lot about what the cars, what their state representation is and everything as we go. So first of all, this is a very high fidelity driving simulator. Like I said, there's esports competitions on it. It models things like aerodynamics and slipstream effects and tire traction and track conditions. To the point where there was a movie out recently called Gran Turismo, where somebody who was trained in the video game only went on to become a champion or a top-notch professional race car driver with real cars. And this video really gets across how high fidelity the simulator is. So what you're seeing here is an expert driver, Ken Chan, in the bottom part driving a real car on a real track, and in the top part driving that same simulated car on the same simulated track in Gran Turismo. And he's trying to drive it the same way. And in the real car, obviously he's sitting in there and using a steering wheel. Also, as you'll see later in the talk, when he's driving the simulated car, he's in a similar setup where he's sitting in a place driving, accelerating with his feet, using a steering wheel. And the key here is that when he finished this lap in the simulator, he was within 1/10 of a second of the time that it took him to finish the lap in the real world. And here you can see it sort of time aligned. He's taking the same line, and the car is controlling in the simulator almost exactly the same way that it controls in the real world. So our challenge was to do this against some of the top drivers in the world, and we did this. We challenged 4 of the top drivers shown here. This was during COVID, so we were limited. We couldn't bring people from all over the world, but it happened that 4 of the best drivers at Gran Turismo were in Japan, and so we were able to bring them together. And we challenged them to a race on 3 different car track combinations. So if you actually follow Formula One racing, you'll recognize these tracks: the Dragon Trail Seaside, the Lago Maggiore track, and then the famous Cirque de Sarthe, which is where the 24-hour Le Mans happens. Just to let you know, this is a question that often comes up. We, just like these people here, practiced with these cars on these tracks. We also let the AI agent practice with these cars on these tracks. So we trained a separate agent to control the car on each of these track car combinations. That's something that we've relaxed since then. So now we actually have a policy that can generalize across tracks and cars, and I'll talk more about that later. But for the purpose of this race, we gave the AI agent the same advantage that people have of practicing over and over again on the same track. And the reason this says July and October is, as you'll see, we raced against them in July of 2021 and ended up losing. Then went back to the drawing board and fixed some things. And in October of 2021, we ended up beating these people, and handily. So I'll show you that. So how did we do it? What's the approach? So first of all, I'll tell you what some of the challenges to solve are. I already mentioned that it's a real-time control task. So the steering wheel is moved in real time. So it's 10 times a second that there's sort of accelerations and decelerations, and the steering wheel commands are accepted by the API. People actually can act more at a higher rate than that. So there's a little bit of a disadvantage to the AI agent in terms of the frequency of action decisions. But you're really operating at the edge. You have to be, if you go a little bit faster, the car is likely to spin out. If you go a little bit slower, you lose all of your advantage. So you really have to be able to get a deep understanding of the car dynamics and racing lines and control the car with precision. That's if you're racing on an empty track, but that's not all. It's actually a multi-agent setting, because there are other cars on the track, and so you have to figure out when to pass them and when to block them from passing. When to use, there's sort of complex maneuvers that I'll talk about, like slipstream passing and crossover passing. I'll show you examples. And then finally, one of the most sort of intriguing aspects is that there's a complex etiquette to racing that's not really well defined. There's a human judge, a human steward, who sort of enforces the rules of etiquette and sportsmanship, and we had to somehow encode that into the agent. So the high level approach was really an end-to-end deep reinforcement learning approach, where this is the typical reinforcement learning environment where or diagram where the agent is sending actions, throttle, steering, and brake, to the environment, getting a reward and then a new state, and just continuing in this loop. And when we started out on this research, I actually thought that this would be a task for model predictive control more, that where you would want to sort of figure out what's the line that the car should follow, and then use use a plan or a model of the car dynamics and the plan to figure out how do you stay on that line. And I think that was the conventional wisdom at the time. And we were surprised to, even though we tried that approach, it did not work nearly as well as this end-to-end deep reinforcement learning approach. And when I say end-to-end, I mean, it literally started out with random behavior where the car is just taking random actions. So it's driving off the track, running into walls, going in circles, not making any forward progress. And then, with a lot of experience, is able to get to superhuman levels, as I'll describe. So to answer one of the questions, or one of the questions that came up in the chat already, some of the details of the control interface. The actions are simply brake or throttle. So it's a two-dimensional action space at 10 hertz. So -1 is full brake, +1 is full throttle, and the car can be anywhere in between there. -1 is full left, +1 is full right, and you can also set the steering wheel anywhere in between there. The rewards for when you're driving on an empty track is simply just how much progress you make in a time step, perpendicular to the center line of the track. And then we added some penalties for the tires slipping or going off the course or hitting a wall. When we get to the multi-agents part of this, where the tactics come in, I'll tell you how we augmented the reward function in that case. And then for the Nature paper, for the first iteration of this, the state space was not the pixels of the camera, which is what people use. We have, in follow-up work since then, we have used the pixels as the state features, and shown that is possible as well, that the car can control itself from the pixels. But instead, in the first iteration, we gave it an API that sort of distills down the state to the kinds of features that a person would experience as well. And we tried to be fair about this. So things like the velocity along the X, Y, and Z axes, and the acceleration, the roll, pitch, and yaw of the car, the loads on the tires, the tire slip angles, and then things like the car progress along the track. So first of all, there was a number from 0 to 1 saying, is it at the beginning or the end of the track? That's a track specific feature. And then we also gave some sort of points along the track that show the shape upcoming, and that's a track independent feature, so that we were able to generalize across tracks later in an extension of this research. And so here, this video sort of side by side shows the car is in green over here while it's driving. The purple is the points that we would send to it. It's the distance and angle to the left, center, and right of the track for 60 points spaced in front of where the car currently is. And so you see that sort of tracking its state progression as it's driving around the track. Okay, so I mentioned that a lot of this had to do with the compute infrastructure. We had the advantage of partnering with Sony Interactive Entertainment, which had a bank of lots and lots of PS4s, PlayStations, which were not used especially at night. I think they're used for sort of a cloud service, and there's times of day when they're underused. And so we got access to a big bank of them for training. And so we could create in sort of a standard actor critic kind of method. We could use rollout workers that's getting lots of experience, state action reward tuples that then get a selection of which get passed into an experience replay buffer. And then we train on GPUs a actor and a critic. So the critic is a queue function. The actor is a policy. I'll tell some more details about that. And one of the sort of nuggets of contribution here was that we developed a new distributional reinforcement learning algorithm called QRSAC, which stands for Quantile Regression Soft Actor Critic. So if you know, I'll have a slide of details of this on the next slide, I believe. But it's not just learning the expected value of taking an action, but the full distribution of what's the worst that could happen up to the best that could happen, binned into a quantized 32 bins. We also used n-step returns, so we found that not just doing a one-step backup of what the effect of your action is, but looking ahead at least about a half second into the future makes a difference. And this is showing the numbers here are the best lap times of an agent when it's using standard soft actor critic and QRSAC, so almost a second improvement, which is a big deal on an empty track on Lake Maggiore. And we found that the sweet spot for sort of the look ahead and backups was about 5. That was less of an innovation. The end step look aheads was a known sort of technique to use in RL. But this is for those of you who know RL, this might be a little technical for people who don't already know reinforcement learning. But this is just one slide of the technical details of QRShack. So it learns 2 different Q functions using end step returns to then the 2 is so that we to mitigate maximization bias, and then it uses a Huber loss to on the buckets, which is also makes a difference compared to some of the other possible loss functions. And then there's a policy objective function, which is just trying to figure out which actions are going to lead to the best predictions of rewards in sort of a standard actor critic kind of way. Again, the full details of this are in the paper. And then one more slide of details for those of you who are interested. The neural net training architecture had the input state features, the 2 outputs. It's actually just 2. There shouldn't be the dots there. There's the throttle and the steering, and then it was 4 layers of fully connected with a double, twice as high learning rate for the critic than for the actor, and some dropout and clipped gradients. All the details are again described in our Nature paper. But so to actually get a feel for how this did, here's what happens. Here's what it looks like after 1 hour of training, and 1 hour means getting. We can put 20 cars on a single track, and we had, I think, 10 PlayStations in creating experiences. So sort of 1 hour of real time means about 20 hours of car experience. But here's what it looks like after 1 hour, 4 hours, 8 hours, and sort of in the final version of training. So after 1 hour, it's it is driving forwards, but not very efficiently. It's wobbling around a lot. It's going sort of slowly. By 4 hours, it's doing a little bit better. 8 hours, a lot more efficiently. And by the end, it's a superhuman performance. It's driving around the track faster than the best people. And let's see, I see a question here. So, so did you embed any prior knowledge about the physics of the environment? No, there's nothing. There's no model here. This really is just end-to-end deep reinforcement learning, and it's having to learn the effects of its actions in a model-free kind of way. Now, the more general part of that question that Tristan asks is, do I believe in pure scaling of learning algorithms as the main path forward for AI? And no, I would not generalize that that's always the best approach. It's worked surprisingly well in this case, but I wouldn't say that's always the right thing to do. But in this case, yeah, there was no physics, no world model given. It's a model-free algorithm. So just to quantify, these blue lines here is a histogram of the best human times recorded on a platform, Kudos Prime, where people record their times. So this is like the best time ever recorded on the Lake Maggiore track was in the 115-second range. And this is, the orange is, and most of the best times were in the 120-second range. And this is how well GT Sophie does after 4 hours, 8 hours, or 24 hours, and also how well the built-in AI, the AI that came with Gran Turismo prior to GT Sophie, how well it did. And then this graph is showing a histogram of GT Sophie's best 100 times, because there is some noise, and then the mean times of the top 5 people. And so again, the best GT Sophie's scores are pretty equivalent to the best person, and significantly better than the second through fifth place people. And that was on Lake Maggiore. The other 2 tracks, Sophie's sample times were significantly better than the best people. So in this case, we would say it's not superhuman because it's about in the same ballpark as the best human. But on the other 2 track car combinations, it was significantly superhuman. And so then we can ask the question of where is the AI better? You'll see this in a video. Here's Igor, one of the top human drivers, and this is showing sort of color coded with the track where GT Sophie. This is his time, how far behind GT Sophie he is. So at the beginning, he's sort of doing just as well as GT Sophie, but then he falls behind in this chicane. He falls behind here. He falls behind at this, more at this circle, at this hairpin turn, and then again over here. So GT Sophie is finding sort of better driving lines. There's not much of an advantage on the straightaways, but at the sort of curves in the track is where it's doing better. Oops. Um, and so here's a good way of sort of visualizing that. I think in this video, if I recall correctly, you can sort of see, listen to Igor talking.
It gets way more difficult to do the same things.
And actually, before I'm saying this, you can barely see in the front of the video, there's a ghost, which is GT Sophie. That's the car controlled by GT Sophie. And Igor is trying to follow GT Sophie. So he's trying to see if he can follow the line that GT Sophie takes. So I'll start it from the beginning. You can listen to his commentary and his observations of trying to, in this case, learn something from the car.
We don't have the same precision, so it gets way more difficult to do the same things, and they can react like very, very quickly.
You see him trying to catch up to the car, but it isn't quite able to.
Man, that's fast. That's really fast. Like, I really want to watch the onboard as well to see how like they throttle and you know, braking trace, steering trace as well. It work, because it's definitely something else.
So this was an early experience where he's saying basically, I'm learning something from the car. I'd like to be able to learn more. And you know, he was very, very impressed by it.
They don't have the same precision, so
how do I'm trying to move to the next slide here. Sorry.
It gets way more difficult to do the same things, and they can react like very, very quickly.
Sorry, for some reason I've lost control over the slides. Let's see if I. Sorry, let me try reloading this.
We don't have the same precision, so
sorry about this. There should be a control.
It gets.
No, that's not what I wanted to do. Huh. Haven't had this problem before. Sorry about that. Let's see. Oh, okay. Oh, I see. I'm in the wrong. Okay, if I go here. There we go. Okay, sorry about that. So one of the questions that came up, and this was, you know, is this fair? So, you know, is the car? So if you remember, like, you know, in the Jeopardy challenge, people talked about how the AI agent had faster faster sort of reaction time than people did, and that's why I was able to use the buzzer and get into questions quicker. And so, you know, we were asked, is it that GT Sophie has less latency than people have? And it turns out that, you know, that people have about 250 milliseconds latency between what they see in the screen and you know, what they can act, how they can act in as a result. And so we actually we tested GT Sophie with adding delays, where we, like, you know, made sure that there was a delay of the state feed up to 250 milliseconds, and even so, it was able to still reach superhuman performance. So this is one of the things that the Nature reviewers required us to test. And also, humans are using the steering wheel and the pedals more smoothly. So the blue line here is sort of the how a person is controlling the car, whereas the orange line, because it can only change the actions at every tenth of a second, is what the agent learned to do. But you see that there's sort of much more fast or bigger changes that GT Sophie uses. That's something we actually got rid of later. We enforced a sort of a smoothness constraint. But this is sort of, in some ways, an advantage for the people. There's a faster control rate. I can't remember what this video shows.
I think there was a lot from the like the AI.
This was just Igor saying that he's learning from that he was learning from it, which you already sort of got the sense of. Okay, let me see. There was a question here in the chat as well. Let's see if that's okay. That's a long one, so I'm gonna hold off on that for a little bit, and come back to it if there's time, or if somebody wants to, Stas, if you want to summarize it for me at some point. But let me keep going. So what I've talked about so far was sort of demonstrating how the car does on a empty track, but that's only one of the, 1/3 of the problem in some sense. There's also the multi-agent aspect and the etiquette aspect. So first of all, we played around a lot with what would be the representation for representing other cars. And we came up with just sort of a slot filler notation, where up to a certain distance, we say, what's the distance, the relative position, velocity, and acceleration of the cars in front of you and behind you. So this is like, the closest car to you, the second closest car to you, third car, if there is one within a range. And then we also added a reward term for sort of collection of experience that the car would be trained on. So we didn't just train it in sort of random scenarios. We first of all, like I said, we could simulate 20 cars at a time. So we put
Recording in progress.
Means to drive in traffic and to try to pass people. And we also created situations where it's immediately behind another car in a straightaway, so it can learn to do a slipstream pass, which means basically like drafting that bicyclists do. You get in the where there's less air resistance behind the car, and this is modeled in the simulator. You get extra momentum, and then you sort of bounce out from behind the car, and you can use that extra momentum to pass. Or crossover passes where you sort of take the line that's shown here. And so so that's sort of, we created situations that, again, would expose these kinds of tactical scenarios to the car. And then one of the key innovations here was, it's a particular type of sampling from the experience replay buffer, where we generated all that different experience. And then as a function of where the car was in the track, it would curate the sort of proportion of experiences that the car was learning from at that part of the track in that course position, based on sort of different types of experience that were collected by the rollout workers. And this was done manually for the 2022 paper. Since then, we've come up with ways of automating this. And we do actually stratified sampling. So when I show the proportion here, it's not just that it creates a big pool with this mix of data and then samples from it randomly, but it actually makes sure that the right proportion of data is sampled from each of these bands when it's training the car at that point in the track. So here's some examples of some of the skills that are learned. So this is the slipstream.
Now we've got the second part then of this straight. This is one of the best overtaking opportunities because, of course, you've got the advantage of the slipstream, but you need to do it on the straight. You can't do it going into the braking zone because there isn't one. And you can see that Orange knows that, goes towards the outside line, and is ahead then of Tomoaki Yamanaka as they come in towards Indianapolis. So it's the Sophie AI system ahead of Tomoaki Yamanaka. So it's Miyazono from AI, from Yamanaka from AI.
And that got stopped there, but that why did that get stopped?
Now we've got the second part then of this straight. This is from AI, from Yamanaka, from AI.
It ends. It's so that was showing actually that what happened was that it did the slipstream pass and followed, but it was actually trying to block the slipstream pass. So I'll come back to that scenario later on, but here's some of the additional scenarios that I told you about, sort of the rolling starts, the chicanes where there's sort of little bends in the track, corners and slipstreams. Here's an example of a defensive maneuver. So you'll see GT Sophie, the colored one again, with the 4 human drivers behind, trying to stop them from passing it.
Hold their line and hold firm against the AI, but it certainly proved to be a tougher challenge than I should imagine that they were thinking. Emerald goes defensive then. Miyazono tries to get the switch back on the inside. No opportunity presents itself through turn 3 then.
So basically, it's not taking the optimal line on an empty track, but rather picking a line that would make it hard to pass. And then here's, I think, my favorite skill. It's the double crossover pass. So on the left, you'll see the real cars. On the right, you'll see sort of an animation. And you'll see that GT Sophie, 2 of the cars, sort of let themselves get into a position where they're behind the human drivers coming into a corner, but they've learned to be able to take a line that
we go once again a defensive move there from Emerald, but losing 2, losing 3 position there for Emerald. Oh, and contact there as well, as I think Miyazono got a bit of a hit from Grease. Grease goes up into P5. Here comes Emerald on the outside.
So you see that they started behind, but then after that turn, they ended up in front. So so these are the kinds of skills that they learn in the multi-agent setting. And then finally, there's this last challenge, which I told you about, which is the sort of the etiquette aspect. And racing etiquette, there's sort of these subtle, imprecise sportsmanship rules where there's an incident means some occurrence or a series of occurrences involving one or more drivers, which causes an avoidable collision, but nobody defines what avoidable means, or forced a driver off the track, but again, no definition of forced, or does something that's illegitimate, but again, no definition of that. And so, and when that happens, a steward can impose a 10-second penalty, which means that the car has to slow down and for 10 seconds, which gives a huge advantage to the opponents. And so we had to try to somehow encode this in the car, and to get a sense of the how important this is. Here's a situation from the July race, the one we ended up losing, and we analyzed it very closely because, as you'll hear the announcer say, it looks like GT Sophie is way ahead, and that there's no chance for the person to pass. But then the person is actually able to pass, and it's because we found out later GT Sophie hits the brakes because it's too timid. It's worried that there's going to be a collision, and provides the opportunity for the person to pass.
It is very, very interesting, and this is proving to be a very exciting climax to the race. And it's going to make things very interesting in terms of the overall point standings then here as well. We come through Arnage. That was the last real overtaking opportunity then for Sophie Orange. But is Yamanaka going to try and invent something down into the Porsche curves? You bet he is. What a move then from Tomoaki Yamanaka to get it ahead. Orange runs it a bit wide through that.
So there you see, like the announcer was surprised that there was and you could see the control, how the human driver is driving in the side there. But the announcer was surprised that he was able to pass. And when we did the analysis afterwards, it was because the car was too timid. And then on the flip side, the car can be too aggressive as well.
Cockburn, these guys need to be working together really at this stage, because look at Orange really close onto the back. Was there a bit of contact into the left-hander? I think there was. Cockburn pushed onto the gravel and losing a position.
So we had to somehow train the agent not to do these things. And so we added extra penalties and tried to operationalize as much as we could who's at fault. So you're always at fault if you're the one who pushed who bumps in from the back. If it's a collision from the side, it might not be your fault. So we gave more penalties for ones that you're at fault, the ones that you would probably be penalized for, and small penalties for any collision. But this was a sort of a reward engineering exercise to try to get the weights just right. And then there's a final aspect, which was actually more interesting than we thought, was the choosing the driver. Because of course we used this end-to-end reinforcement learning to train the car, many different instances of the car, but then when we put it in the race, we had to pick just one. And so to do that, we got several different candidate instances, and then checked that they could, that they had some skills that we defined, so these different agents, and we rated them on, could they do slipstream passing, and can they go fast enough again around the turns and stuff like that. And then we did a head-to-head competition against the best ones and ranked them. But then we had a human expert come in and drive against them and tell us whether they thought they were too aggressive or too timid, and then picked one that may not have been the one that did best in the head-to-head competition to race in the race. And one thing we found just 2 weeks before the first competition against people, we ended up being told that the agent that we had selected was way too aggressive and was going to get penalized a lot. And so we had to sort of, it was sort of nerve-wracking for us to manually decide which is the one we're gonna go with. And in the end, we picked one that was pretty good, but it didn't beat the people. The way the race was is there were 4 GT Sophie agents and 4 human drivers. The GT Sophie agents were not told which cars are other GT Sophie agents and which ones are human drivers. They were all indistinguishable. So there was no opportunity for collusion or sort of cooperation among the GT Sophie agents. The human drivers could have. They were told not to, but they knew which ones were GT Sophie and which ones weren't. And then the point scoring was you got 10 points for finishing first place, 8 for second, 6, 5, 4, 3, 2, 1 for the other 4 places. And we ended up losing. We won in one of the races, but lost in the other 2. We did double points for the Cirque de la Sarthe because that's the hardest one, and so lost by a little bit. And so then we went back and tried to analyze what went wrong. There were a couple times when the car lost control. It also lost some positions at the start, so it always often came out of the starting blocks at a disadvantage. I already showed you the place where it gave way unnecessarily because it was too timid. And there were also times when it was, behind another car. We know that we're faster than that car, but it wasn't for some reason closing the gap, using the speed to close the gap. And so we sort of analyzed that. In the July 2nd race, we actually had two different policies that were stitched together. The one that we used for the empty track and the one that was trained for close interactions when there are other cars near each other. And the one for the open track is faster, but it wasn't as good at the head-to-head interactions. And so we had this sort of switch point between them. And that was a source of a lot of the problems. Switching the network out would cause this lack of this sort of spin out where it's getting closer to the other cars. And when it gets to the point where it was going to make the switch, it just sort of mysteriously spun out. There was nothing that caused that. And that was just because of these stitched together policies didn't interact very well together. So we had to sort of, we had to figure that out. In the end, by the rematch, we were able to create a unified policy that was a little bit wider and I think same depth, but the network was a little wider, and it was actually able to outperform either of the other two. So we didn't have that problem anymore. We also gave some extra practice for the starts.
2021 is underway.
And so this is what the starts look like, the rolling starts, where the cars are all sort of bunched up together. And so we trained some extra, gave some extra training experience for that, so that the cars wouldn't sort of get blown away right at the beginning. I'm not going to show too much there. And it also mattered, we improved the opponent population for training. So agents in the July race, they hadn't practiced against representative opponents. They had only, they hadn't really practiced against people. They'd only practiced against the built-in AIs. And so for the rematch, we included the July agents, and that made a big difference. There were sort of higher quality agents to train against. And so, we found that if we trained just against the built-in AIs, that we ended up with a very aggressive agent that was overconfident. If we only trained against aggressive opponents, it became overly cautious. But if we sort of got the right mix of the built-in AIs, some line followers that we hand-coded to be ones, and then other GT Sophie policies, that's how we got the best mix of being both sportsmanlike and fast. I didn't show you the last start, so the starts were chaotic. I'm going to skip through a couple of these videos, but it ended up doing much better at the start. It did a lot better at closing the distances. So in July, we found out that it just didn't have that much experience with cars that were 70 to 75 meters ahead of it. And so when it got into that situation, it didn't have the data, it didn't know what to do. And so it would take a long time to sort of close that gap. And so we gave it more experience of cars in different places. And then here's this same situation where the car was too timid before, but instead we get the reverse, where GT Sophie was 7 seconds back and was able to pass the person and then stay in the lead. So you can sort of see the difference here. So again, GT Sophie's the red car behind the person, and now being just the right amount of aggressive, trying to get in the slipstream. The person is moving around to make it so it's hard to get into the slipstream. If GT Sophie is able to do it, and then is able to sort of edge around the person, and then get a line here where after this next turn is in the lead, and then never looked back and never gave up the lead in this race. And so when we got to the October 20th rematch, this time GT Sophie won all 3 of the races. I think had positions 1 and 2 in all 3 of the races, and outscored the people by double. And so here are the actual scores. Finished in 1st, 2nd, 4th, and 5th place in 2 of the races, 1st, 2nd, 5th, and 6th place in the other 2. This is a graph of sort of how far the different people and the other GT agents are behind the leader as the race goes on. And so that's that was the story as of now, almost 3 years ago. In February of 2022, we got the result published on the cover of Nature. But then since then, there's been a lot of more recent developments, and so I'll use the rest of the talk to sort of tell you, and it's actually now turned into, I think, the most widely deployed reinforcement learning agent out there. There's hundreds of thousands of people that can interact with it. If you have a PlayStation 5 and the game Gran Turismo, you can race against GT Sophie. But we had to, not just make the best, the superhuman agent. That wouldn't be very fun. So we had to spend another year sort of trying to make it a fun agent to race against. And then once we released it, we got a whole bunch of really good testimonials and and the take. These were testimonials from people who raced against the champion version. And actually, this is a nice video from Emily Jones. I'll let you listen to as well, because she says that she's learning from the agent.
It was really interesting seeing the lines where the AI would go. So there were certain corners that I was going out wide and then cutting back in, and the AI was going like in the whole way around. So I learnt a lot about the lines, and also knowing what to prioritize. Like the AI into turn 1, for example, I was braking later than the AI, but the AI would get a much better exit than me and beat me to the next corner. So I didn't notice that until I saw the AI, and I was like, oh, okay, cool, I should do that instead.
So she's learning from it, which was really nice to see. So our takeaway is here that the single control policy was better than trying to differentiate skills. The specialized scenarios mattered, that the etiquette was the big challenge, and top racers really appreciate having an AI that's competitive. So we then went on to, we did create a version for in GT7. The original one was done in GT Sport, a previous version. We got feedback from the community and let people, the general public race against it. And then we tried to make it fun, and we actually got it into a permanent feature of the game. So this was GT Sophie 2.0 for all PlayStation 5 players. It can now handle lots of cars, lots of tracks. It's many more than 9 now. We're trying to get to all of them. Lots of different tire types, and so it's a much more general agent. And then people have in the game playing, social media and magazines and things have reviewed it and given a lot of really positive feedback, that it's much more fun to race against than the previous version. And so, like I said, that when we got it into the permanent feature of the game, it's able to control many more cars, many more tracks. And if it all runs locally on the PlayStation. There's no cloud running. It's not running in the cloud, so it's downloaded the whole policy on your team. And then there's a bunch of interesting challenges. So we did not address the pitting, when to pit, and dealing with different weathers. Although that's something we've been looking at since. Explainability and interpretability, more strategic decision making. And trying to generalize to other domains. We've done some of that. There have been some follow-up papers now. My favorite, I like this video because one of the things we're looking at now is allowing the car to drive with different styles. And so we changed the reward function. Here we added a reward rather than a penalty for tire slipping or for drifting. And we ended up with a racing policy that does this. So to go around current corners now, it sort of does some extra drifting. And drives with sort of a style that you would never see a person do. Does that sort of 360 and then makes it around the turn. So again, this is work that fantastic people at Sony AI. And with that, I'll stop here. There's a few minutes for questions if people like to discuss. I'll try to read the long comment in the chat that was there while people are unmuting or typing things in. But with just before I do that, I'll remind you that this is all within the context of my overall research question of what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains. And there's much more about some of my other research if you go to my webpage and click on courses and talks. There's some online talks that talk about some of the other stuff going on in my lab that I invite you to take a look at. So there's a question here. How do we adjust the difficulty for players of different skill levels? That one sort of easy way to do that is to give GT Sophie a different car, right? So if you're driving, the person's driving a Porsche and I'm driving a Camry or something like that, GT Sophie's driving a Camry, then that's going to adjust the level of difficulty. And so that's the thing we did in the first version of the release. But and so there's beginner mode, intermediate mode, advanced mode, depending on the car that you were controlling. But there's now we've actually made it so that we can control it using sort of within the reinforcement learning agent, telling it to pay attention to different different aspects. If we make it be more courteous, for example, that'll make it slower. If we make it more aggressive, that'll make it faster, and then that can make it more difficult for different people. And so we've sort of exposed those now, and we're experimenting with a version that the expert drivers don't actually have to control their car when racing against GT Sophie, but rather they can provide sort of high level coaching advice to GT Sophie to change what it does, and that can also make it sort of a different level of difficulty. The next question there is, how do we quantify what's fun for a human to play against? That's not us, actually. The people at Polyphony Digital who designed the game, this is a labor of love. They've been working on it. The CEO of that company has worked on it for more than 20 years. It's sort of an art to them, and they look at it, and we'll provide them a potential GT Sophie agent, and they'll look at it and say, nope, you can't deploy that because it's shaking the steering wheel too much. That doesn't look very realistic, or doesn't look human, or it's too aggressive. That's not going to be fun. So in some sense, we were sort of trying to, they have a utility function in their head that they are not able to write down for us, that we keep having to adjust for. We give them an agent, they tell us what they don't like about it, and then we have to try to create a new reward function that will make it more fun, more something that they're willing to put out in the game. And so that was a long drawn out process, and it's we've sort of internalized a lot of it now, but that's something that's it was definitely a challenge between creating a very fast agent and creating a fun agent. I see a question on how big an influence was the advantage of not being controlled by smooth control. So that actually wasn't a big deal. The fact that you could sort of move the steering wheel almost instantly to a new position, that was one of the things that they wanted us to stop doing before we released it, because they said it wasn't a matter of a fun as much as just like if people saw the steering wheel moving too quickly, they would consider that unrealistic. So we had to prevent the agent from doing that, and we were able. That didn't make a huge difference in the best times that it was able to do. It's just when there was nothing preventing it from doing it, it would add this sort of artifact, this behavior, but it wasn't giving much of an advantage. And then there's so a question: can the same system be applied to training a robot in a virtual war environment? So possibly, often I get the question is, could this apply on a real car? And you wouldn't be able to do exactly this on a real car, because we started from random behavior. So you would ruin a whole bunch of cars, which doesn't matter in the simulator, but would matter with real cars. And also we require a lot of training data. It's possible that using a sim to real kind of approach, you'd be able to do something useful. But that's not something that we've looked at. I do know that there's at least one Formula One racing team that's using, has re-implemented GT Sophie and is trying to use it within their system, but they can't. They can't tell us many details about what they're doing, so we don't know yet if it's been useful for them. But certainly, using this kind of approach in other simulated environments is possible. And like I said, we've had some follow-up papers where we've experimented with using QRSAC and effectively the same algorithm in sort of some more toy reinforcement learning domains, things like the Lunar Lander and some grid worlds and things like that, where we can experiment with trying to automate that. And so if you look on my website, and some of these same authors, you can find some NeurIPS papers and ICML papers that are follow up from this work, and including one from last year at the Reinforcement Learning Conference, where we learned with the pixels as the input space, as opposed to the state features that I told you about. Let's see. The only other chat comment here, I see this long one from Thomas. Let's see if he said it's not really a question. So, yeah,
just a comment. It's not a question.
Okay, good. And then, were there any problems that affected the time of when the agent was able to drive at time? I'm sorry, I don't actually understand what you're asking there. Do you want to unmute and try and explain, or try again?
Sorry about that. I was asking, was there any problems like within the simulator that like affected like the time that like y'all got now? Like, was there anything in the simulator that like really messed it up and it was causing like problems for y'all to like get a deep understanding like learning?
If I understand correctly, I mean the simulator itself was I mean, we had to engineer it so that we could get lots of data from it. I mean, there's definitely, if we change the tires on the car, or we change the weather or anything like that, that makes it so that the car is the same policy doesn't work. So you need to train it under those different conditions. But I'm not sure if that's exactly what you're asking. I mean, the simulator itself is very, very robust. And we didn't really uncover. I don't think we uncovered any bugs in the simulator itself. We've now been applying RL to other games, other PlayStation games, and there we have sometimes uncovered some things that the developers weren't aware of. But I don't think we ever did in this case. Let's see. Building on my previous question, did it affect the policy when utilizing constraints? Also, for applying the constraint, did you just use clipping and add constraints in the Lagrangian? No. So what we did is what we have been experimenting is with using sort of a universal value function approximation method, UVFA, where you can train an agent to not just do one thing but be goal conditioned. And so the same policy can, as I said before, sort of be more courteous or more aggressive, or you can change the reward function, and then at deployment time say, here's what your reward function is now, adjust your policy accordingly. And that's a way that we could make it controllable, and so that's turned out to be a very powerful method. Let's see. I mentioned that the released version of GT Sophie runs locally on PlayStations. Does this have a heavy performance effect on the user running the game? No, it doesn't. So we've had to distill down the policy and make it very lightweight. Of course, it's the training that does a lot of the compute. But then once we have the policy, we're able to deploy it onto the PlayStation console. There's of course a memory budget and a compute budget. And we're not allowed to exceed that, so that it doesn't degrade the performance of the game, and it doesn't. So if you have it, you can play with it, and you'll see that the people are still getting exactly the same performance, the same real time control over the car, and they're racing against the agent. And the challenge there was, unlike in this talk, we had to generalize. So we've trained the agents to work with different cars. We pass now as inputs features of what car they're controlling, and features of the track, so that because we can't afford to put a different policy for every car track combination onto the console. So it's really forced us to tackle the generalization challenge. So I think those are the questions I see there. If anybody wants to unmute, I can take maybe one or two more, but otherwise,
any last questions? Okay. Thank you very much for your presentation. It's great. Yeah, it's amazing. But just it looks like a lot of reward engineering. How long I know you need to design reward. It's in this task. Is it difficult? Or
so it's not. I mean, the reward function in the end is not that complex. And if you see, there's, like I said, it's mainly progress along the track. there is, and then there's some penalties for the sort of the etiquette and for like to encourage passing and I think that the reward function was we've had to play with a little bit, but I wouldn't say that it's that brittle, and that's not the big issue. I think a bigger issue is the curating of experience that goes into the experience replay buffer. And we've worked on methods. One of our NeurIPS papers as a follow-up is a method that a method we call event tables that sort of automatically defines the events that you want to have extra experience for, and then sort of picks the right proportion of experience for each of those events to put into the experience replay buffer. And so that we've sort of because that was a very laborious manual process to come up with that graph of what's the sampling proportion of the different experience, and so automating that was pretty important for us. But for the reward function design, I think it's been a little bit incremental, but it's not super. That's not super sensitive.
I see. Okay. Thank you very much, and
yeah. Thanks again for inviting me.
Great work. Yeah. Thank you, Peter.
All right. So long. Thanks for coming, Daniel. Good to see you.
Same here. Thanks for the talk. Very interesting.
Pleasure.
Recording stopped.